Hey guys, just a bit of a code review of a modification of, it's called motion detection. I'm not quite sure what it's trying to do actually. So we're doing a delta between a series of frames. I've got a sequence of these already separated from a video stream. I've only got about 10 frames of it, so it doesn't do much. Most of this is just set up, setting up a window, loading the font so it's a bit bigger so we can see it on screen. And these are from the original example. These are some threshold size, which I'm not quite sure what that's meant to do. And a filter size, which we're not using initially. Let's just run the program up front. So we processed the 10 frames and we're doing deltas between the two, and the highlights, the white highlights, are whatever the equation is for the threshold. So let's have a look at the code. The main difference is that this one loads each frame once. So initially we load a pair of frames because we have to. And then after the initial loop, we're just loading a new frame every time. And we're keeping so out of the pair of frames, our frame 1 and 2, we're keeping frame 2, and that becomes frame 1 next time. So we're comparing this frame with the future frame, and then we're comparing the future frame with the one after that, etc. So that's the process there, and the load process here, doing a bit of work in those things. So we're loading the thing as an effects image. We're scaling it to an absolute size, which is what the 1 represents here. We're doing a grayscale of it. In other words, we're just converting all of the color information into all the RGBs to monochromatic, pretty much. So in that format, all the colors are like this, like a sample color. They would all be, if the level was 200, then the red, green, and the blue will all be 200. We don't need that. So if we mask off everything but the blue channel on the bottom, we can then use that to our advantage in a minute and use the color as an index into a pre-computed array, which is how the routine works. So that's our loading process. We'll jump up back to our little routine. Where are we? This is the main loop. Just running through a sequence of frames, loading the current frame, and comparing the frame, and then displaying the actual RGB information, which is why it's a blue tinge, because we've removed the other color information from it. But we're creating a mask from it. That's the only bit here that's kind of interesting. This is a bit more convoluted to do this, but we're trying to make sure that we only ever read from one image at a time, and we can do that by grabbing rows of pixels from one image and copying them to a temporary array, and then using the array to do the access. So it saves us having to change surfaces all the time. You could double the performance of the way the routine was by simply doing this. Like in the original routine, I just made a little mock-up in a loop. It was X to width, whatever. Sorry. But then it was going render to image 1, give me this RGB from a point, X loop, Y loop, whatever. I'll call it point 1 actually, RGB 1. And then it was reading from the other alternate image, so we're comparing two images together, the same coordinate from the image. Now the images have similarities between them, they're the same size, so we could just compute an offset and fetch them both from the raw memory if we wanted to. But we're talking about images here in PlayBASIC. Now what you could do, if you wanted to keep that model, is you could go, well, this switching backwards and forwards between surfaces is very slow in itself. So to halve that, you could go, well, let's step across here we'll go step 2, and I'll read a pair of pixels, RGB 1A. It's pretty clunky, I know, but here. So what we're actually doing, I'll probably compute that here. So we're halving the switching between surfaces. So the more we unroll this here, then if the surface is not perfectly a width of 2 or 4 or whatever you're going to unroll it to, if this was 4, we'd have 4 of these. It's a very common way of improving the performance of most routines, because loops they're not pretty in terms of performance. They're quite expensive actually. Doesn't matter what your language is, a loop is an expensive process. That one there would probably give you the best bang for this method, even though that's not a great method. But what we can do is because we're still reading these pixels individually from the surface, running them through the PV runtime. What we could do is go, hey, what if I just copy a row from the source image or the last frame into a temporary array, which is what this convoluted mess down here is doing. So we're locking the last frame, we're getting a raw address of it, and the pitch, which is the number of bytes on a row. The mask is irrelevant to this part of the conversation. We're declaring an array which is twice the width just for safety reasons, really. It doesn't need to be twice the width. We're getting a pointer to this array. Now these are integers, right? 32-bit integers. Nothing special about the values inside an array at all. Same as colors. There's nothing special about the colors inside those things. As long as you understand the format of the makeup of the pixels, that's all we care about, right? We know they're integers. We know they're in a grid-like fashion for in an image. So we can just copy those things to a one-dimensional array. We can't do it with multiple dimensions of arrays because they have like a scattered format. It's a different conversation. But that's perfect for 1D. So all we need to grab a row from that source texture, source image. It saves us having to switch forward and back. So in our main processing loop here, to grab a row full of pixels, we're using copy memory. Now this is a much more optimal method than doing this by hand, because that's pretty much an unrolled copy loop in assembly language. That's what you're calling. There's a point where it actually becomes irrelevant speed-wise, because if you're copying a very small amount of memory like this, then it's probably slower than doing a peek and poke, and that's because you've got all of the setup code. But for big amounts of data, like a row of pixels, like it's going to be 4K of data or something like that, because these frames, the images here are, I think in the source sequence of frames, they're full HD, so they're 1920 wide by 1080, but we're scaling them down to screen size, which is about 1024, so it's still 4K width. So we can do this, which is going to copy that 4K in a fraction of the time we could do that by doing a peek and a poke or trying to read the points from it. No matter how we unroll that code, it would still be pretty inefficient. There are other ways you can do it too, but they're paling to significance against theirs. So the actual processing loop now becomes, we're stepping through the current frame, reading a point as you would expect. Now the point is the RGB color. Those RGB colors have been, the red's gone, the blue's gone, the green's gone, and the alpha channel's gone. So all that's left over is the blue intensity. Because in grayscale images, the red, green, and the blue, they're all the same value. That's all they are. So we don't need the value repeated, just need it once. Now, when we read from row, we're reading the pixel at the same location on this image from a previous frame. Now, rather than doing a calculation, I'm just putting the two values into a table, which I've pre-computed up front, which has all of the possible outcomes for this combination, and it writes them into the 2D mask. I mean, this itself, if you unrolled this loop itself, you could gain extra performance over what this does. So because again, a 4-next loop, every loop structure has overhead in it. It doesn't matter what language you're talking about, how optimal you think your programs are, they're not. Every looping construct has overhead. So if you want absolute performance on anything, then you've got to unroll things. Most compilers will actually do this for you. People just don't realise this. They think, oh, it's quicker than what it used to be. Well, actually it's not, because the compilers run through your code and copied and pasted the inner part of the loop into multiples of 4 or 8. So when you optimize for speed and you don't mind about big the execution of your the application becoming large, that's what it's doing. It'll pull functions in that are only used once or twice, inline them, etc., which can be fantastic for the performance of some routines on some systems, but it can be very detrimental for others. But in general, unrolling loops is a wise way to go. Here I haven't bothered, because I think we're pretty much we're not at an optimal performance for this process, but we're probably somewhere approaching that. In other words, the speedouts we get from here are small percentage gains rather than big percentage gains, because all we're interested in is getting the thing to run at a reasonable rate. Before, it was probably doing a frame a second. Now we're probably doing a couple of frames per second. So we've made a big improvement, but it's never going to run, at 50 frames per second. It's not going to happen. If I grab my video editing software and try and apply an effect to it that does a filter, that's not what happens. It crawls. It literally crawls. Anyway, I mean, what you could do for this kind of thing, if you're really interested in this kind of per pixel processing, is scale these things down to 50% their original size, and use a filtered scale. So sort of keep most of the important information in the frame, and then you can't, because scaling is a bilinear filtered mode. Where are we? Where's the scale image stuff? Down here. Go across to help. Just hit F1 on the command. That mode flag there, if you set it to say a particular size or a percentage and use bilinear filtering, filtering means that you're going to add you're going to lose some color quality, but that's par for the course as far as I'm concerned, really. If you could halve the size of the frame, do your processing. By halving the size of the frame, that's a quarter of the pixel data you've got to process. So if you can make it run a couple of frames per second with a full frame, then you're talking about multiplying its performance by 4. There's another part of the program too that's doing a filter. I don't get what the filter's trying to do. I have no idea. But it's much slower. It was rendering circles over the top of the threshold though. I don't get what they're meant to be doing. But we're still in that probably 1 second per frame. We're doing a filter of, I think it's 16 pixels around each pixel, and then it does a tally of all the set pixels, or all the pixels in the mask that was set, and if it's above a certain point, we draw a circle there. I don't know why, but that's what we're doing. I guess that's the first step of another step there as well, but I don't know. I don't really know the goal of what we're trying to do, or what Scott's trying to do. Anyway, that'll do us, dudes. Codes in the forum, etc. Pick and abuse it all you like. I don't give a crap. But that's my thinking about how to approach this kind of problem in general. there are ways around these things, and they're a little bit more, lower level than what people might want, but they're solvable. We probably do need I know in the graphics libraries, there are functions that will read a row of pixels from a source, and that's probably what we need to have as a public command, actually. Like, if you could do that, this logic here would just turn to, you could grab a row of pixels from the last frame and put them in an array. So you still need an array to place this stuff. This inner loop here would probably stay the same. Actually, maybe it's probably better to read a row from the last, read the current row from the last frame, read the current row from the current frame, and then do a comparison in here and get rid of the point statement. So you've got effectively just a bunch of array lookups inside here. Yeah, don't know. You have to check it. I have to check that out, fire that stuff up. Anyway, dudes, thanks for listening to my waffle, and I'll see you later. Bye.